Lagrangian mean quadratic makes us less worried about this exotic local. Right? If Lagrangian contains higher order interaction term, then we have to worry about this complicated behavior. But if it's quadratic, then I avoided discussing about non-abelian gauge theory because of the presence of ghost. The ghost is very complicated, so in order to understand that, you have to take a proper course about quantum physics. But since I'm given only 4 hours, I tried to avoid it. Now let's start the computation of determinants. This is really tedious, but as you will see later, all we need is some knowledge about SU2 commutation relation. Do you know what the SU2B algebra is? All of you know. And the representation theory. All of you know about. Okay. All we need is just that. It's very surprising. But before starting the computation of determinant, let's review some basic geometry about Ram's sphere. And I set the radius to M. Okay. So the most intuitive way to define this space is by this equation. This equation embedded in flat 4-dimensional space. So this is actually giving you units here. And with this equation, I define the Riemann metric like this. Then what I will get is the radius around the sphere of radius L. Okay. So this is a parameterization of sphere in terms of 4 coordinates obeying one equation. But instead of this, I can also do the following thing. Introducing what is called Euler angle. I introduced theta and phi and chi. Okay, and this equation is automatically satisfied by this equation. And then if I plug in this definition into this Riemann metric, what I will get is, you can check this. And this is not going to be a very complicated exercise. So this is the metric on the round sphere written in terms of Euler angles. And now, if you are given this form for the Riemann metric, then from this you can set. Maybe you think that the natural or the most natural way to define the field by modeling is given this metric, then if you set the field line like this, then you can easily check this equality. Okay? Yeah. But it turns out that this way is not the most convenient way. So let me introduce another way to choose the field line manifold. There is another way which makes use of the Maure-Cartan manifold. Another way. So to explain this another way, let's define a 2x2 matrix defined by this. So this, defined like this. So more explicitly, the 2x2 matrix has this component. Okay, so let's think about this 2x2 matrix. Actually, if you use this equation, this matrix is shown to be an element of SU2. Okay, first of all, you can check that this matrix has determinant 1, and also this matrix multiplied by the Hermite conjugate of itself gives identity matrix. So this is an element of SU. So what I'm talking about here is the equivalence that the three-dimensional sphere and the group manifold of SU2 are the same. Now, if you are given this matrix G, let me define the following quantity G inverse Dg. So this is one form taking value in the 2x2 matrices. And actually this turns out to be a linear combination of the gamma matrices. And let me define the coefficient of gamma 1, 2, 3 by A. So this is a one form, the triplet of one form. Right. And it's a standard exercise to compute mu1, mu2, mu3. Let me not write them down, except for just the mu3. You can just work out. So this is the expression for the mu3. So you can work out the expression for the other two. Okay. So instead of choosing the field line forms like this, what I'm proposing here is to choose the field line bundle as L times these Maure-Cartan forms. So this is Maure-Cartan. Okay, so this is much more convenient choice. Why is this? Well, actually this mu satisfies a very beautiful relation with respect to the derivative. derivative of mu1 is just a product of mu2 and mu3. And we have another two equation which is just a cyclic pound equation. Okay, so or if I use the Levitch-Vickers symbol, I can rewrite this equation in this way. Are there questions? No questions? Okay. So if you have this equation, then it turns out to be very easy to compute the spin connection. So this is the SO3 valued connection, which I have introduced in my last lecture. And then the definition for the spin connection is via this equation. And if you make the comparison of this equation and this equation, where UA is related to EA of this equation, then what you find is that this spin connection is just given by this. Okay. Am I too slow? So since now we have the expression for the spin connection, we can talk about the killing spinner. And I can just show you the explicit solution to the killing spinner equation. So killing spinner equation takes this form. So this is the differential form notation of the covariant derivative acting on spinner field. And the killing spinner equation says that this has to be equal to some gamma matrix multiplied onto the same. Okay, so this is the killing spinner equation, and what does the solution look like? Well, so now we have found the expression for the killing spin connection, so let's insert this expression here. Then this box. Then if you make use of the identity about the three-dimensional harmonics, so this second term in the left-hand side can be rewritten in this manner. Now let's look at the whole equation. In this term and this term on the right-hand side and this term on the left-hand side is identical. So the killing spinner equation just boils down to this. So if you choose the field by one form to be like this, then it turns out that the killing spinner is just given by the constant. So this is another reason why this choice is very good. If you make another choice, for example, the choice given here, then the expression for the killing spinner will be much more complicated. So it depends on the choice of local Lorentz spread. What's the importance of this solution to the killing spinner equation? So since there is a killing spinner around the sphere by making use of the formalism I have explained to you last time, I can construct supersymmetric theory from round sphere. If there is no solution, I cannot do that. So this is important. But for later purpose, what is going to be more important is killing vector. So killing vector is the generator, the vector field which generates the symmetry of the curved manifold. Okay. So S3 has SO4 symmetry. This is obvious. So since in one way of defining the S3, we made use of the 4 coordinate x0, 1, 2, 3. So and the equation is invariant under the rotation, right? So S3 has SO4 symmetry, and SO4, as you know, can be related as a product of two SU2 coordinates. And these two copies of SU2 act on the 2 by 2 matrix G from the left hand side. So there is going to be a triplet of vector field corresponding to the left action of SU2, and there is also a triplet of another killing vector field corresponding to the right action of SU2. Okay. And I'm going to write those killing vector like this. So this is the generator of left SU2. This is the generator of right SU2. And I'm going to use the standard normalization for the killing vector field so that, for example, RA and RB obey this commutation relation. So this is the standard commutation relation for the SU2, right? Okay. So I want to know the explicit form of this left action of the killing vector field for the left action of SU2 and right action. So there is a very nice trick to define the expression for this killing vector field in terms of coordinates. Okay. So now let's recall. Okay, let's start with this very fundamental quantity d. So this is dxn and the this can be further written like this, adjusted inside of the field 1 and inverse field 1. So this is what I denoted like dA. So what I want to know is what is this vector field. So let's name this vector field by XA, and let's find out the property of this vector field. But if we try acting this operator D to the 2 by 2 matrix G, Then this can be rewritten like this. This is again a trivial rewriting, and this was actually this thing is related to the linear combination of the field by one form field like this. So if I look into these expressions very carefully, what I find is that the action of this vector field X on this 2 by 2 matrix field, 2 by 2 matrix G is just a multiplication of this 2 by 2 matrix from the right. Okay. And I recall that gamma matrices divided by 2 is a doublet representation of this. Then the end result is that this vector field is actually proportional to the generator of right action of SU2. And the proportionality constant is this. Okay. So this result is going to be very important, because this kind of differential operator makes appearance very often in these expressions. So what I'm going to do next is to make use of this relation between the differential operator and the SU2 generator, and rewrite this operator in terms of SU2 representations. So the determinant of wave operator, the problem of the determinant of wave operator turns into the problem of some SU2 SU2 operator. Okay. I have some 6 minutes before lunch, so I have right. So what I want to compute is this. So I have to compute many determinants. So in the remaining 6 minutes, let's try to do this computation in the first determinant. So this is the most basic one. Questions? So let's compute the determinant of Laplace operator for the matter field phi. This operator. So the result is that if I make use of the correspondence given here, this can be related as a determinant of this operator. looked very complicated. We have to solve the differential equation, but now we found out that this wave operator can be rewritten in terms of SU2 generator. So this is simply the Casimir of SU2. You know what the eigenvalues of this operator is. So very easy. So let me rewrite this further. Just the rewrite. Okay. So now is the time for me to use some knowledge, some fact about the spherical harmonics on 3 sphere rather than 2 sphere. Maybe many of you know quite a bit about the spherical harmonics on S2. So you can imagine that there are similar things also on 3-dimensional spheres. Okay, so let's use the fact about the S2 spherical harmonics. There are eigenfunctions of such operators, and those eigenfunctions are labeled by a spin of SU2 L on the right. And there is a constraint on the spin of those eigenfunctions under the SU2 left and right. The constraint is that the SU2 left and the SU2 right spins have to be equal. This is only constraint. So if you have a spherical harmonics which falls into the representation of SU2 left and right with these quantum numbers, then you can immediately compute this eigenvalue. RA is just a square of the spin. So usually it is J times J plus 1, but since J is N over 2, you have this. Then all you have to do is to just insert this here. Let's do this one. Before doing so there are eigenfunctions with this eigenvalue. And how many of such eigenfunctions? Well, in spin J representation, there are 2J plus 1 states, right? So the eigenfunctions of this eigenvalue, there are N plus 1 times A plus 1 eigenfunctions. So this is the multiplicity. Okay. Now the result for the determinant is just the product over the non-negative integers n. I'm just computing the expression appearing here. I just inserted this in here. So this is the result.